Hi everyone. Today we are going to discuss about bipolar junction transistor in the course of basic electronics. We all know that in our mobiles, computers, in everywhere we use ICs. Do you know ICs are made up of transistors, and IC is consist of so many transistors of the order of 1 million transistors in one IC. So today we are going to discuss about the transistor, that is the basic functional part of integrated circuit, that is IC. So in today's class we are going to discuss about the syllabus of this course and introduction to bipolar junction transistor, BJT, that is bipolar junction transistor operation, and the bipolar junction transistor configurations. In today's class, we are not going to discuss about tutorials, BJT biasing, and etc. Because of the time constraint, we are going to discuss about only just introduction to bipolar junction transistor and BJT operation. So the reference books for this course are very famous books. One is Electronic Devices and Circuit Theory by Ballstedt and Nashle, and one more is Integrated Electronics by Milman and Archias. So let us discuss about the introduction. A solid-state transistor was invented by a team of scientists at Bell Laboratories during 1947 and 48. This team consists of Bardeen, Cooper, and Stripper. These are the three scientists who invented this transistor. These transistors bring an end to vacuum tube era, because now our computers are just very, very small in size. That means they can be put somewhere on the desk, or so many compact computers are there, even laptop also there. But if we think about computers in 1970s or 1965 or around 1970, a computer occupies a lot of space. That means one computer occupies a small, let us say 10 feet by 10 feet room. That means very large in size. It consumes lot of energy to run that one, because they are made up of vacuum tubes. But with the invention of transistor, the computer size or electronic gadget sizes comes on reducing, because the transistor is in smaller size. They are lightweight. No heating elements are required like vacuum tubes. They consume very low power, and operating voltages of the transistor is very low. And the price, and one more thing, the price of the transistor is very less. Here in the left figure we can see different transistor packages. That means plastic package and metal packages. Apart from that, these are different types of transistors. One is BC. This is BC 107 transistor. This has a gain of the order of 150, and this one is a power amplifier. This one is SL100 transistor. Like this, so many transistors are there. The advantage of this metal case is they can radiate the heat efficiently when compared to these plastic packages. So this is an IC. As we have discussed already, an IC is equivalent to a million of transistors. This is an IC. These are also an IC. These are also an IC. This is light emitting diode. We can observe that the IC is almost of same size of our transistor. So bipolar junction transistor is a sandwich consisting of three layers. of different types of semiconductors, as shown in the following figure. Two kinds of BJT sandwiches are there. One is NPN and the other one is PNP. So if we observe in this figure here, this is a p-type semiconductor. This is called emitter block. This is a p-type semiconductor. This is called collector, and this one is a n-type semiconductor, which is called as base. So among these three, the base is of very narrow width, and collector and emitter are all almost have same width, but when compared to collector, the emitter will be having large, very little high width. So this is PNP transistor. That means if we take a p-type semiconductor, we make in between we sandwich a n-type semiconductor. By using this arrangement, we can get two junctions. One is here, this is emitter, this is base. Here we can get emitter base junction, that is emitter base. This junction acts as a diode, one diode, and we will get one more junction, that is base and collector junction, that is this one. So this base collector junction acts as one more diode. But here we have to remember one thing, that this emitter base will be always to get to the amplification, that means to get the proper operation of the transistor, we should get this emitter base should be always in forward bias, and this base collector junction should be always in reverse bias. So in the same way, when you take when a p-type semiconductor is sandwiched between two n-type semiconductors, we will get NPN transistor. The working of these two types of transistor will be almost same. So so the three layers of BJT are called emitter, base, and collector, as we discussed. Base is very thin compared to the other two layers. Base is lightly doped, emitter is heavily doped, collector is moderately doped. So NPN in NPN transistor, emitter and collector are made up of n-type semiconductors, and base is a p-type. Whereas in p-type PNP transistor, emitter and collector are p-type, base is a n-type. So both NPN and PNP transistors are extensively used by electronic industry. Both types we can use interchangeably. There is no problem. Next, coming to transistor symbols. This is a symbol for an NPN transistor, and this is the symbol for PNP transistor. As you may observe here that there is no difference except this arrow mark here downside. This arrow mark is upside. This arrow mark tells you the conventional flow of current direction. Conventional flow of current direction means when the electrons moves like in this direction, the current flows in this direction. That is just conventional direction. So both are almost same, but the current flowing direction is different. BJT has two junctions, emitter base junction and the collector base junction, analogous to two diodes connected back to back, because transistor is nothing but a sandwiching of two diodes connected back to back. One is one is emitter based diode, the other one is collector based diode. So the device is called as bipolar junction transistor because in a transistor, that is a conventional transistor, we have two junctions. One is emitter based junction, the other one is collector based junction. These two junctions, because of two junctions, we are calling as junction transistor. And bipolar means in bipolar junction transistor, the current transfer takes place because of free electrons and holes. Electrons are electrons are negatively charged carriers, and holes are positively charged carriers. Because of these electrons and holes, the current transfer is happening. That's why we are calling it as bipolar junction transistor as bipolar. Bipolar means two. We have to remember that one. Next, let us come to the operation of the transistor. Operation of NPN transistor is discussed here in the next diagram. Operation of NPN, operation of PNP is similar with roles of free electrons and holes interchanged. There won't be any big change. Just you have to remember the operation of NPN and PNP transistor will be almost same, but the roles of electrons and holes will be interchanged. For normal operation, as we have discussed, emitter-based junction should be forward biased and collector-based junction should be reverse biased. So when you consider a PNP transistor or NPN transistor, whatever it is, in common base configuration, emitter-based junction will be forward biased. Because of that one, in emitter-based junction, the width of the depletion region, that is emitter-based junction depletion region, will be very, very narrow. When come to reverse biased common base junction, it is reverse biased. That's why the depletion region width is maximum or wide. In this one, let us go to discuss about the transistor operation. Here, no resistors have been shown. Just for understanding, we are showing here. So this is a N-type now we are discussing about NPN transistor. This is a N-type transistor. Sorry, N-type semiconductor. That means in N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. There also will be immobile ions. Okay. Now we are discussing the case without any bias. Later we discuss about bias after applying some voltage. What happens? So now we are discussing about without applying any voltage. Just remember, in N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. There will be immobile ions, positive ions will be there. In P-type holes are the majority carriers and electrons are the minority carriers. Immobile ions also will be there. They are negative ions. Here you might have observed here very less number of holes have been shown because this P-type region, P-type semiconductor width is very, very less. That's why we have shown just 2 electrons. Here 6 electrons, here also 6 electrons. In N-type collector, because it's a N-type semiconductor, majority carriers will be holes, electrons, and immobile ions will be there. Minority carriers are electrons. This is a picture. Now what we are going to do is we are applying biasing conditions. That means this emitter base is forward biased because if you observe the battery of this VEB, this is a battery. This VE means the voltage applied per emitter. Subscript B means it is common base. That's why this subscript stands for. That means voltage applied to emitter in common base. Okay. So this is a battery. This is a battery. So what happens here? Emitter is N-type semiconductor. We are connecting a negative of the battery to N-type and positive of the battery to P-type. So this junction will be forward bias. In this case, we are connecting positive of the battery to N-type semiconductor and the negative of the battery to P-type semiconductor. That's why this junction will be reverse biased. And here the depletion region will be here. If you consider there in depletion region, electron holes recombination will happen. Because of that one, there won't be any electrons holes. Only negative ions, positive ions will be there both sides. So this is called depletion region. Here you can observe this width of the depletion region is more in reverse bias. Here the depletion region width will be less. So like this we have to give give bias to discuss about the transistor operation. This diagram shows that three regions of transistor. Here you can observe that emitter and collector are at both same Fermi energy, that means same chemical potential, but our base will be a little bit higher chemical potential. Because of that, there will be a barrier from this. This is a barrier. This will be approximately 0.7 electron volts for silicon. If you take the transistor is made up of silicon, we can tell that this barrier height will be approximately 0.7 electron volts. Here also same thing happens. This barrier height also will be 0.7 electron volts. This is a NPN bipolar transistor we have shown here. Here, in this side also free electrons will be there. This side also free electrons will be there. In this base, what happens here? Very less number of electrons will be there. That means here holes will be there. So this is the symbol of our NPN transistor. The arrow shows down. That means this is an NPN transistor. This is base, this is collector, and this is emitter. This is without applying any bias. Just remember, this diagram is for without applying any bias. This is the diagram. After applying the biasing, that means after applying the voltage for emitter base junction and collector base junction, what happens? This is the diagram. So now what we are doing here, we are not applying any voltage to base emitter junction. Just we are applying voltage of 10 volts to base collector junction. That's why what happens, this potential or chemical potential of this electrons will be still reduced. That means these electrons can flow easily from this side to this side only when they cross this much barrier. This is a barrier. That's why we always call it as base as a control switch. That means a switch kind of thing. That's why when these electrons crosses this barrier, they can easily move to collector region. So this is the other diagram. When both the junctions are biased. In this one, you can observe we have applied a voltage of 0.5 volts between base emitter and 10 volts between base collector junction. In this diagram, we can observe this barrier height is reduced. That means electrons can easily flow from this side to easily travel from this side to this side. That means the current will be high in this case. But whereas in this case, the current will be very, very less, almost of microamperes. So here CP junction is reverse biased and increased barrier height. Whereas here emitter base junction is forward biased. Here the collector base junction is reverse biased. That's why charge flow happens very easily. Here we have to remember one thing. Here what happens? The electrons from this side to this electrons flow from this side to this side. At the same time, what happens in p-type semiconductors? Holes are the majority carriers. When these electrons flow from this side to this side, there is a possibility of recombination of electrons and holes. This will constitute the base current. Base current. Emitter current means the current flowing from emitter to emitter to base. And here, because of recombination of electrons and holes, this constitutes a current that is called base current. That is IB. We represent it with IB. We represent this emitter current with I subscript E. And after this recombination, some maximum portion of electrons comes to collector. This constitutes collector current. This will be base current will be very, very less. So because of electron hole recombination or combination, leads to small base current. So here this is the explanation about the transistor operation. When emitter base junction is forward bias, free electrons from emitter region drift towards base region. Some free electrons combine with holes in the base to form small base current. Inside the base region p-type, free electrons are magnetic carriers. So most of the free electrons are swept away into the collector region due to the reverse bias collector base junction. So now we are going to discuss about the different current components in the transistor. What are the different current components in the transistor? As we have discussed, that is I subscript E, that is emitter current. I subscript B, that is base current. I subscript B, that is collector current. So we discuss one by one. So coming to emitter current is due to the flow of free electrons from emitter to base. This results a current from base to emitter. Coming to base current is due to combination of free electrons and holes in the base region, as we have discussed. But the magnitude of this current will be very, very less, of the order of microamperes. But coming to current, collector current, it has two components. One is due to the flow of electrons from emitter to collector, that is one component. The other one is due to thermally generated carriers. Because of heat, some carriers also will be generated within the emitter base. Because of the flow of electrons also, it constitutes a current. That current is called as thermally generated minority carriers. So here in this diagram we have shown the directions of the currents of each currents. So if you consider this is emitter current, because this is emitter, this is base, this is collector. As we have discussed already, emitter current will be the summation of base current and the collector current. So emitter current will be equal to this one and this one. According to Kirchhoff's law, this current will be equal to this one and this one. That's why this one base current will be in this direction, collector current will be in this direction, and the whole emitter current will be in this direction. So otherwise in PNP transistor, the current direction will be reverse. So base current will be in this direction, collector current will be in this direction, and the emitter current will be in this direction. So note the current directions in PNP and NPN transistors. For both the varieties, this equation holds good. As noted earlier, collector current has two components. One due to the injected charge carriers from emitter. Another due to the thermally generated minority carriers. Both results in current in the same direction. Hence, IC is equal to alpha DC plus, IC is equal to alpha DC into IE plus ICBO, where ICBO is the current due to thermally generated carriers. IE is the current because of injection charge carriers from the emitter. So here the alpha DC is the fraction of charge carriers emitted from emitter that enters into the collector region. ICBO is the reverse saturation current in the CB diode, that is collected base diode. So from this equation, that is IC is equal to alpha DC into IC plus ICBO, we can write alpha DC as like this. Alpha DC is equal to IC minus ICBO divided by IE. So here we have to remember one thing, that ICBO is very, very less when compared to IE and IC. Hence we can approximate this equation. We can approximate this equation like this. IC is equal to alpha DC into IE. We can write alpha DC is equal to IC by IE, whereas where we call alpha DC as common base DC current gain. Current gain means how much input current we are giving, how much output current is coming out. From that one we can calculate the current gain. So the value of alpha DC will be always less than 1. It will be around 0.95 to 0.99. Why? Actually, already we have discussed IE is equal to IB plus IC. IB will be very, very less when compared to this IB and IC. Sorry, IE and IC. That's why what happens, these are almost same, but this IC will be a little bit less when compared to IE. That's why alpha DC will be always less than 1. That's why alpha DC value will be always around 0.9 to 0.99. That depends on the type of transistor what we are taking. Here are some mathematical calculations are there to simplify the equations. Since the value of alpha DC is around 0.99, ICEO will be very, very greater than when compared to ICBO. Now we are discussing about common emitter configuration. Okay. In common emitter configuration, as we have discussed earlier, in common base configuration, the thermally generated current in common emitter configuration, that is ICEO, will be very, very greater than ICBO, that is thermally generated current, because of common base configuration. However, ICO is still very small when compared to IC. Just remember that one. Hence, the approximation will be like IC is equal to here beta DC, where beta DC is the DC current gain for common emitter configuration. So IC is equal to beta DC into IB, or beta DC is equal to IC by IB. This will be very, very high when compared to alpha DC, because here just remember that one thing, that is IB will be very, very less when compared to IC. Let us say, for example, IC is equal to let us say 0.99 amperes, sorry, 0.99 milliamperes, and IB is equal to 0.1 milliamperes. Then what happens? If you calculate IC by IB, that is equal to 0.99 divided by 0.1, it comes around 99. So beta DC will be 99, and alpha DC will be around 0.95 or 0.99. So from this one we can come to a conclusion that beta DC is very, very large when compared to alpha DC. So parameter beta DC is called as common emitter DC current gain. So values of alpha DC and beta DC vary from transistor to transistor. That is common thing. So both DC, alpha DC and beta DC are very sensitive to temperature changes. So when we have taken a computer or electronic gadget, whatever it is, if you take the computer to a AC, the function of that computer will be very good. Otherwise, if you keep it outside and using, heat will be generated. That's why the performance of the computer will be less. This is because of this temperature generated currents. Now let us discuss about some problems. So the first problem is a BJT has alpha DC 0.998 and a collector to base reverse saturation current is 1 microampere. If the emitter current is 5 milliamperes, calculate the collector and base currents. Just you try to calculate these values. The answers are like 4.99 milliampere and 10 microampere. This is collector current is 4.99 milliamperes and base current will be 10 microamperes. Next one, next problem is an NPN transistor has collector current 4 milliamperes and base current 10 microamperes. Calculate the value of alpha and beta, that is alpha DC and beta DC values of a transistor. Here we are neglecting the currents, that is thermally generated currents, that is ICBO or ICO. The answers will be alpha DC value will be 0.9975 and beta DC value will be around 100. Just try to calculate. If you have any doubts, in tomorrow class we will discuss and we will come to conclusion. And the third one is, in a transistor, 99% of the carriers injected into the base cross over to the collector region. If the collector current is 4 milliamp and collector leakage current is 6 microamp, calculate the emitter and base currents. This is the main formulas we have to use here is, first one, as we have discussed, IE is equal to IB plus IC, that is the first equation. Next, coming to alpha DC is equal to IC divided by IE, and beta DC is equal to IC by IB. You have to use these equations and you have to work out these problems. If you have any doubts, we will discuss in the tomorrow class. So BJT has the 3 terminals. For 2 port applications, one of the BJT terminals need to be made common between input and output. So according to this 2 ports, which terminal is common? According to that, we can arrive at 3 configurations. That is common base configuration, common emitter configuration, common collector configuration. So the last one will be, we are not going to discuss the last one, because in this one the common collector configuration, voltage gain will be very, very high. That's okay, but current gain will be very, very less. So if you multiply both of them, will come to a power gain that will be also less. In common base configuration, the current gain will be high and the voltage gain will be less. This we can use in some applications of electronics industry. In common emitter configuration, current gain will be high and voltage gain will be also high. If you multiply both of them, we will get a large number, that is power gain. That's why we use common transistor in common emitter configuration is preferable. That means we are, in all power amplifiers we use transistors in common emitter configuration. Just remember that one. Now let us discuss about common base configuration. So common base configuration is shown below. Here we are not showing any resistors, just for understanding purpose we are discussing. Here this is base, this is emitter, and this is collector. So base is common between input and output. This is input circuit, this is output circuit. Base is common between both of them. Here the input voltage is VEB. This is the battery we have connected between base and emitter. This is the input voltage, and the battery that we have been connected between base and collector is VCB. So VCB is the output voltage. The input current will be IE, because this is the current flow. This is the direction of the current flow, but IE is the input current and IC is the output current. This is common base configuration. So in common base configuration, the input characteristics of the transistor will be like this. We take VEB on x-axis and IE on y-axis. If we plot VEB versus IE for different output voltages, VECB 0, VCB 10 volts, VCB 20 volts, we get curves like this. This diagram is called as input characteristics of transistor in common base configuration. So a plot of IE versus VEB for various values of VCB is shown in figure. It is similar to forward bias diode characteristics, because the in forward bias, the diode characteristics also are same as like this. That's why they are similar to common base transistor or common base transistor. Input characteristics will be similar to our junction diode forward bias characteristics. As VCB increases, IE increases only slightly. Here you observe in this diagram, when we increase VCB, here it is 0, here it is 10 volts, here it is 20 volts. But you observe for different, for the same value of, let us say, let us take a particular value of, let us say here it is 9 volts. If you take, if you draw a line on this one, this is the emitter current for 0 volts, 0 volts of VCB. This will be the emitter current of for VCB 10 volts. This will be current for like this. If you observe, the variation of emitter current is very, very less when we are changing the collector base junction voltage, that is reverse bias junction voltage. So here we have to note that the letter B is suffix B is for common base configuration. So for common base configuration, the input characteristics are two. One is the input resistance, Ri is equal to delta VEB divided by delta IE with VCB constant. Here we have to keep VCB constant. This is called as input resistance, Ri. Next one is voltage amplification factor. That means how much per a particular IE current, how much output voltage is there, how much input voltage we have applied. This is VCB is output voltage, VEB is the input voltage. So here delta will be there. That means the change in for a particular value of for a particular variation of VEB, how much variation of VCB is there, that we have to measure. That is called as voltage amplification factor. AB is equal to delta VCB divided by delta VEB with keeping constant IE. Both can be determined from common base input characteristics of the transistor. Here, just for calculation purpose, it has been shown. We have already discussed. So we have taken this one for a particular VCB value. So for two different values of VEB, that is VEB1 and VEB2, we have taken the values of IE. For VEB1, the current value, that current is IE1. For VEB2, the current is IE2. From this one, we calculate input resistance, that is Ri is equal to VEB1 minus VEB2 divided by IE1 minus IE2. This will give you the input resistance. When coming to the voltage amplification factor, that is AV, we have to fix a collector current, input current, that is IE. At the same input current, for different values of VEB, what are the values of VCB, that we have to measure. By finding out this values of VCB1 and VCB2, VEB1 and VEB2, we can calculate AV is equal to VCB1 minus VCB2 divided by VEB1 minus VEB2. By using these formulas, we can calculate the input parameters, that is Ri and the AV of a transistor in common base configuration. Next, coming to these are some observations. Common base output characteristics are a plot of IC versus VCB for various values of IE. Three regions are identified, that is active region, cutoff region, saturation region. In this next diagram, it has been shown here. We will explain that. This active region, for active region, emitter base junction should be forward biased, collector base junction should be reverse biased, and IC should be positive, VCB should be also positive. So IC when we increases IC, IE increases. So for a given IC and IE values, almost constant, increasing only slightly with increasing of VCB. This is due to the base width modulation called as early effect. This is the output characteristics of this diagram shows output characteristics of transistor in common base configuration. Here, three regions have been highlighted. Just observe. This blue portion is saturation region. This brown portion or gray portion is cutoff region, and this is the active region. Okay, so the transistor has to work in this region only. Then only the transistor will be in operation. Otherwise, in cutoff region or saturation region, the transistor acts as a switch. That means if you apply some voltage, it goes to one stage, it doesn't come back. That is called as switch. To switch the the operation, we have to give some external triggering. Then only it switches between cutoff region and saturation region. So without doing that, the transistor will be in always working condition when it is working in the active region. So these are the different regions of our common base transistor output characteristics. So base width, when coming to base width modulation, as the reverse bias voltage VCB is increased, the depletion region width at the CB junction increases. This is common. Part of this depletion region lies in the base layer, so effective base width decreases, hence the number of electron hole combination at the base decreases, so base current reduces and collector current increases. Here we have to note that I is equal to IC plus IB. This is common equation. When I is equal to 0, IC also, what happens from the equation of IC, that is I is equal to IC plus IB. When I is equal to 0, IC becomes ICB obviously. ICB is the collector to base current with emitter open. Below this line, we have cutoff region here. Here both the junctions are reverse bias. That means emitter base junction is reverse bias and collector base junction also reverse bias. Then the transistor works in cutoff region. So region to the left of y-axis, that is this one, this region. So region to the left of y-axis, that is VCB negative, is saturation region. Here both junctions will be forward bias. So here what happens, IC decreases exponentially and eventually changes the direction. Here we have to remember on this one thing. In the starting lecture itself, I told that emitter base junctions will be always forward biased and collector base junctions will be always reverse biased. That means to get the transistor to work properly, we have to keep emitter base junction in forward bias and the collector base junction in the reverse bias. If both of them in forward bias cutoff region, it will be in cutoff region. If both of them in forward bias, the transistor will be in saturation region. We don't require this one. We require this kind of working only when we want the transistors to act as a switch. Okay, just remember that one. So now coming to output characteristics of the output characteristics parameters. Output resistance RO is equal to delta VCP by delta IC, where I is constant. Current application factor A is equal to, we call it as beta AC, that is equal to delta IC divided by delta E with VCB constant. So both can be measured from output characteristics. This is common. Now let us come to transistor other configuration, that is common emitter configuration. In common emitter configuration, the emitter is common between input and output junctions. That means input and output circuits. So Here emitter is common. This junction should be always forward biased. This junction should be always reverse biased. So now the emitter is common. That's why we are calling this battery as VBE. That means the voltage applied to base with the emitter common. Here we are calling it as VC, where the voltage applied to collector when emitter is common. So the collector we are calling the collector current as IC, and we are calling base current as IB. This is common. So here we have to remember one thing, that is the emitter base junction should be always forward biased, and collector emitter junction should be always reverse biased. So here we have not included any resistors just for simplicity, but when we are doing a practical things, that means experiments, we should always include resistors, one resistor here and one milliammeter here, one resistor here, one milliammeter here. We have to compulsory include, because if you doesn't include resistors, the transistor will get damaged because of excessive current flow. So emitter is common between input and output. The input voltage is VBE and input current is IB. So output voltage is VCE. This is VCE, and output current is IC. This one. Now let us discuss about the input characteristics of common emitter transistor, common emitter configuration transistor. So for this one, we take VB on x-axis and IB on y-axis. So if you plot the characteristics, it will be like this. Anyway, this is similar to a junction diode forward bias characteristics only. This is a plot of IB versus VB for various values of VC. So it is similar to diode characteristics in forward bias. As VC is increased, IB decreases only very slightly. This is due to the base width modulation called early effect. So again, this emitter, this E is for common emitter configuration. Just remember that one. So a plot of IC versus VC for various values of IB is called as output characteristics. In this one, three regions can be identified. One is active region, as we have discussed in common base characteristics. One is active region, the other one is cutoff region, the last one is saturation region. So the conditions for active region are like as follows. It's a linear region of output characteristics. For the active region, the transistor to work in active region, the emitter base junction should be forward biased and collector base junction should be reverse biased. IC should be IC increases with IB. For a given IB, IC increases slightly with increase in VC. This is due to base width modulation called as early effect. This diagram shows the output characteristics of common emitter configuration transistor. As we have discussed, this is cutoff region, this is saturation region, this is active region. So same thing for cutoff region, the transistors both of the junctions will be forward, but when both of the junctions will be reverse biased, the transistor will be in cutoff region. When both of the junctions, that is emitter base and collector base, base emitter junction and the collector emitter junction, when both are forward biased, it will be in saturation region. When base emitter junction is forward biased and the collector emitter junction will be reverse biased, the transistor will be in active region. This is the desired working region of our transistor. That's why we are calling it as active region. So when VC is increased, effectively VCB also increases. For saturation to take place, common base junctions should be collector base junctions should be forward biased. This happens when Vc is approximately 0.3 volts or less for silicon. When Vc is equal to 0.3 volts and Vb is equal to 0.6 volts, Vcb is equal to minus 0.3 volts for forward biased of 0.3 volts. So the region to the left to the vertical line, that is Vc is equal to Vc saturation, that is equal to 0.3 volts for silicon, is considered as saturation region. Region below Ib is equal to 0 line here. Region below Ic is equal to 0, Ib is equal to 0 region. This one is called as cutoff region. So ICEO, that means this is the thermally generated current in common emitter configuration. That's why we are calling it as ICE means common emitter, CE, O means thermally generated current. So ICEO means thermally generated current in common emitter configuration is much larger than ICBO, that is common base thermally generated current, because of the relation ICEO is equal to ICBO divided by alpha DC. But we know that alpha DC will be around 0.99. So the values of alpha DC and alpha AC and alpha DC, beta DC and beta AC are almost same. Hence the subscripts can be omitted for simplicity. From now onwards, we don't call alpha DC, alpha AC. Instead of alpha DC and alpha AC, we just take alpha. That means the current gain in common base configuration. Instead of beta DC, beta AC, we take it just beta, that is current gain in common emitter configuration. So these are the 4 parameters for common emitter configuration. That is input resistance Ri is equal to delta VBE divided by delta IB with Vc is equal to constant. Voltage gain AV is equal to delta Vc by delta VBE with IB constant. Output resistance RO is equal to delta Vc divided by delta IC with IB is equal to constant. Current gain, that is we use these 2 letters interchangeably. A is for current gain or beta also we can take. In most of the books we take A only. In some books they take beta. Anyone we can take. So beta DC or beta AC or A, whatever it is equal to delta IC divided by delta IB with Vc constant. All these parameters can be determined from output characteristics of C configuration transistors. So this is the experimental setup to determine the characteristics of a common emitter configuration transistor, because this is the most widely used configuration for all the devices. So this is the experimental setup for determining the CE characteristics. So if you observe this diagram here, this is emitter is common for input circuit and output circuit. That's why we are calling it as common emitter circuit. And here we have connected a voltmeter, that is we are calling it as the voltage measured by that voltmeter as VBE. Here we have connected one ammeter, that is microammeter. The current measured by this ammeter is called as IB. Here, if you observe, we have connected a voltmeter between emitter and collector. This voltmeter measures the voltage difference or voltage between collector and emitter. Here, we have connected one more ammeter, that is milliammeter here, to measure the collector current. Here we have 2 batteries. One is VCC, the other one is VBB. VCC we use for biasing this emitter collector circuit, and VBB we use for biasing the base and emitter circuit. So here we have used one resistor, that is RB. RB is called as base resistor too, because this base resistor will be of the order of kilo ohms. This we use because of to limit the current, that base current. That means by limiting the base current, we can save the transistor when amounts of current passing through this transistor, it will be damaged. To limit the current, we are using the base resistor, that is RB. It will be of the order of kilo ohms. Next, coming to this RC, this one will be of the order of ohms, 200 to 300 ohms. This is also for limiting the current IC. So this is the entire circuit. This emitter is common between is common for this input circuit and output circuit, and always most probably it will be grounded, so as to reduce any damages happens in when more and more currents go through this emitter base circuit and common base common emitter circuit. So with this, I conclude for today. We will discuss remaining things for tomorrow.